Chemistry time. We are talking, thank you, Gabe, Fiat Lux. Just a little reference from Genesis to get us started. Fiat Lux is Latin for let there be light, and I say that because Gabe turned on the light. Nice. Okay, so we have here already, because we started before I realized we should film this for some of our missing compadres, but we have here already the table that I like to draw for the different kinds of nuclear radiation. We sometimes call these types of problems nuclear reaction, we call them nuclear radiation, but they are different from chemical reactions, even though the way they're expressed is kind of the same. So an example that we have here for alpha radiation, and this, I said this before, but this should be review to you, but it's becoming clear to me that even though this should be review, we might just need a whole class refresher, so here we go. The way we express generally nuclear equation is, let's use an example of the one we already have up here. What if I just were to write this? We've done these problems. We did these in the last video. This substance, this element, is meitnerium, named after Lise Meitner. But what's this 274 represent in the top left corner?
It's ion.
No. The charge goes in the top right corner, which would tell you if it's an ion or not.
It's mass.
It's its mass number, yeah. This number up here is the mass number. So this is not what we're doing today, but you can tell me how many protons, neutrons, and electrons are in meitnerium 274. How many protons? No? 109, is that right? Yep, it is. 109. Nice job. Nice job, Whit. I expected the reason it was taking us a little while is because it's kind of hard to, you have 118 things on there to sort through. So 109 is the number of protons because that's its atomic number from the periodic table. 109. How many neutrons then?
165.
Nice, 165. 165. Electrons? 109. It's always, these two are the same if it isn't an ion, if it's an atom, which this is because it doesn't indicate the charge. Anyway, that's not what we're doing today, but you can do that. This is as a reminder that this number is the mass number. So the mass number is 274. We're going to say that it undergoes, what you would probably be told in your problem is that meitnerium 274 undergoes alpha decay. It would just say that. Meitnerium 274 undergoes alpha decay. I'm even going to write it. Meitnerium 274 undergoes alpha decay. Meitnerium 274, please sit. Meitnerium 274 undergoes alpha decay. So we can do this. There are two different ways. I'm going to show it like I did up here with the kind of, I don't know, longer-winded symbol for an alpha particle. We use this symbol for an alpha particle because an alpha particle is composed of 2 neutrons and 2 protons. So it has a charge of +2 because of the 2 protons, and it has a mass of 4 because 2 protons and 2 neutrons has a charge of 4. But if it has 2 protons, it's also the element helium. But since it has no electrons, it has a +2 charge. So this is one of the ways that we expressed an alpha particle. The other way is just with the symbol alpha. Either is fine. If this is the question, you can write it this way, or you can write meitnerium 274 that. Either of these is a fine way to write it. You should know both, because sometimes you'll be given this and you have to write this. And if you don't know this is an alpha particle, you can't reverse engineer it like that. Then what we do, the actual math comes in, where what is the daughter isotope? So what we do is we know that the mass of an alpha particle is 4, and we know it's leaving this nucleus. So what mathematical operation would that be? Subtraction. So what is our mass going to be after all? 270, because it's 274 minus 4. That's another reason I usually prefer for people who are learning this, which is you guys last year, to use this format for an alpha particle because it tells you the mass is 4. You don't have to have the mass 4 memorized because it already told you it. Anyway, so 270. What will be my new atomic number? It was 109. How many protons have I lost or gained? I've lost 2, right? So now it's borium. So I went back on the periodic table, 2. Borium. Do I have to write the 107 here? I can. It doesn't kill me to do that, but you don't really have to. And then the 2 plus, that just means that it's missing 2 electrons, so there aren't actually a change in electrons, so the charge doesn't change on this. So the answer is borium. The answer is this whole thing. You have to write the whole thing. That's called showing your work. The answer for this one would also be borium-207. Let's label these parts of the equation. What do we call this guy? Or lady, as the case may be. Lee's minor, a woman. I mean, this whole thing is called the something isotope. Nope, try again. Parent isotope. This undergoes or decays or whatever. Nope, this. No. Decay mode, which is also my DJ name. And this one, finally, that's the daughter! Nice. Everyone give Taylor a round of applause. Yeah, do the like basket thing, like, oh yeah, I know I deserve your applause. Okay, so these are the parts you know, and the reason that's important to know those, the things I just wrote in red, is because sometimes your worksheet or the test will say something like, what was the decay mode? You need to do the whole thing still, but you need to write the decay mode was alpha decay, for instance. Okay, so that's the example for alpha. We know that it has a 2+ charge and a mass of 4. Here are its two symbols. There's the example. Give me an example of beta plus decay, Lily Allen.
Bismuth 207.
Okay, bismuth 207.
Undergoes beta plus decay.
Which you can write as this, or I'm going to write these all with the alternate form. You can also write it as an electron. It's a positron. It's an electron. It's the antiparticle of an electron, which is the same kind of form factor, the same excitation in the electromagnetic field, but with a positive charge, which is antimatter. So anyway, so a positron, and what's going to happen here? Well, its charge is going to change, but its mass isn't. So what is my mass number still going to be? Someone who is 207. So it's still going to be 207, but in this case, listen, it's losing a positive charge, which makes its atomic number do what? Go down 1. So now it's lead 207. Peanut butter. Okay. Lead 207. I assume that's right, Lily. Yeah. Lead 207. What's my example for beta minus?
Oh, okay. It's niobium.
In B? Niobium 94 undergoes, I assume, beta minus.
Beta minus and also gamma.
And gamma. Okay.
Wasn't there gamma decay too?
Give me a second. We'll get there in a second. So it's, oh, sorry. Now, an electron is leaving the nucleus. So how does its mass change? Nope. I'm talking about the mass. How does its mass change? It doesn't. So it's still 94. But now, since a negative charge, Taylor's telling us, is leaving, it's the same as it going up 1. So now it's going to be, instead of niobium, it's molybdenum is how the word is pronounced. But yeah. And now check it out. This is also our example for gamma, because the gamma, how does it change the charge? Doesn't. How does it change the mass? It doesn't. No change in either one, and that's what gamma does. Gamma, I don't know, almost like fits in the cracks. Like you can have alpha and gamma decay, and you just write that a gamma decay occurred also, but it doesn't actually change it at all. It's like a diet soda. Yeah, you can drink as much as you want, and all you'll get is stomach cancer. Not a good joke. Okay. Electron capture. Give me an example.
Ruthenium
97.
97.
Ruthenium is Ru. This is the only one that goes on the same side as the parent isotope, because in this case, it's electron capture. An electron is being drawn from the first orbital into the nucleus. So it's adding an electron to the nucleus. Okay, so this time, ruthenium 97, is the mass going to change at all?
No.
So it's bringing in, now it's adding a negative charge. So,
Rhodium.
no, it's going down 1 because it's bringing in a negative charge. It's not exuding a negative charge. It's so the mass didn't change at all, and it's technetium. And then give me another example of gamma. I mean, this one isn't already an example of gamma, but gamma in everything I've seen, it only occurs in conjunction with another one. So we're going to have a double example here.
Oh, wait a minute.
Was that the example?
That one was gamma.
This one was gamma?
That one was gamma.
Lily. Let me rewrite this real quick. I thought it might be. Yeah, thanks, Lily.
Oh,
I was just...
Wrong one.
Lily, it's okay. No one's at blame.
Actually, that was both.
Oh,
It was
I'm at fault. So pretend I didn't just erase
Everybody
that.
is at fault.
Everybody, literally everyone. This is the original sin. This is the fall of man. Questions?
So gamma is also beta?
No, 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 no. No, gamma and beta minus are not the same thing, but this same example is an example of both beta minus and gamma decay. Let's get another example of beta minus that, let me find it myself. This is, someone make the Jeopardy noise, please.
That sucks.
Louder.
Jeopardy.
Someone do the Jeopardy song right now. Do it bad enough that I don't get copyright striked, though. Okay, I got one. Cadmium 113. I don't know why this is making me sweat so much, because this is the kind of nonsense that always is happening, but I feel very unprofessional. Cadmium 113 undergoes beta minus decay and becomes, well, does the mass change?
No.
113. And it's losing a negative charge, so it's becoming, instead of cadmium, it's becoming indium. Indium, which is named after the subcontinent, India. So this one, for the example of gamma, is still also an example of beta minus, but gamma doesn't ever occur just on its own. So there's always going to be something else with gamma. Gamma, as I say, as Taylor says, just like a diet soda, just slips in the cracks. You don't have to worry about it at all. But do make sure you still indicate it. Do you have questions about this in the table that's part of? Do you think you could do the bell work now?
Probably.
Probably everyone agrees. Oh, now I've really messed this thing up.